more.
Okay. So.
Oh, asciugherà. Okay, can.
Okay, so it is my pleasure to introduce the speaker who came for us from very far away, and maybe that's why he was late.
Probably.
So, Professor Emanuele Dalla Torre came here from Italy. My personal guess. Okay. My personal guess is that he was that he sought refuge in Israel because of persecution as a non-Italian, non-coffee drinker.
Yes.
And that he did his PhD with Ehud Altman and his postdoc with Yes, Daimler, exactly. With Daimler, and now he's here in Bar-Ilan.
Thanks, Alan, for the introduction. So, so this is a presentation that I've given in other places. I should give it here as well. Actually, the title is the same as the colloquium that I gave several years ago, but actually all the slides are different. Yes, a couple of years ago. So I think I would like to start actually with a bold statement, which is that quantum computers are a reality. This is a slide that I took from the Quantum Insider, that is a journal, a website and also a company for advising investors in quantum computing. And what you see here, actually this slide is a few years old already, and I added the new row with the Israeli companies. So you can see here, Americas, Europe, Asia, and here I added Israel. What I would like you to take from this slide is two things. First of all, that there are many companies that are actually building quantum computers, and at this stage, most of them, they have a working quantum computer which you can use connecting through the cloud. And the second thing I would like you to take is that there are many different technologies that are being used. So superconducting circuits, silicon impurities, NV centers, trapped ions, neutral atoms, photonics, and it's not clear at the moment which is the one that will bring value to this world. And this is also why so much investments are being made, because you can actually multiply investments for all these in all these directions, because it's not clear at the moment which one will win, and everyone has in mind the silicon that eventually became the standard for all electronic technologies, and those who invested in gallium arsenide, it didn't work for them. So this is the idea.
But the reason that gallium arsenide does not work is nothing to do with science.
Yes, exactly. But also here, it's a technological question. Which is the one that will bring most value, the most value?
Exactly. Silicon was chosen because it's so cheap.
Fine. The price.
Gallium arsenide much better semiconductor.
But also here, the different technology, the different costs. So maybe one is better, but the other is cheaper. But it's not clear which is the cheapest one, because they're all expensive at the moment. So you could say maybe, I don't know, photons are the cheapest. I don't know. They don't. You can just.
Definitely cheaper, but I don't know how.
Right. But the point. But then there are. Yes. Okay. So this whole field really bloomed starting from 2019 with this experiment known as the quantum supremacy experiment by Google. So what it demonstrated is essentially calculation that lasted 200 seconds on the quantum computer, and it would have taken 10,000 years to simulate it on a classical computer. Of course, it's an extrapolation. They did not wait 10,000 years to publish the paper, but it's an extrapolation by taking larger system sizes.
No, but this is not the well-defined. Okay, I'm not criticizing. It's not well-defined person. Because there's also development in classical computers.
Okay, this is this excellent question that will be answered in 2 minutes. So yes, I agree. But at this point, this is what the paper is talking about. I don't want to enter in the details of quantum supremacy. If you're interested, I can explain it in words. Actually, there are not many people who sort of understand what this experiment is about. But in short, what they did, they applied the random circuit and then measured they measured at the end. So when you measure it, you get just random bit strings, like 0, 0, 1, 1, 1. And then you see the probability of the one that you obtain versus the theoretical probability. So if the quantum computer is working as it should, you should have a higher probability of observing those with higher overlap. So that's the game. So you sort of compute because, okay, there are here 53 qubits, so there are 2 to the 53 different options. You cannot probe all of them. You see statistical, which is the one that were measured more probably. And the deep reason why these numbers are so different is probably related to these 2 to the power 53. So as you all know, in a quantum system, if you want to describe a system of 53 bits, classical bits, you just need 53 transistors. But if you want to fully describe a quantum state of 53 degrees of freedom, then you actually need 2 to the 53 complex numbers, because it's superposition of all of them. Okay. So then, a little bit as Sharon mentioned, classical computing has also developed since 2019, and last year, a research team from China demonstrated that they were able to use advanced tensor networks methods, so advanced numerical methods, to simulate the same experiment as the quantum supremacy experiment, basically at the same rate, so even 7 times faster, but same orders of magnitude of velocity. So the point that I would like nevertheless to highlight is that this simulation, classical simulation, required 1,400 GPUs. So it's really, a huge amount of transistors. And if you try to count them, you will see that in each GPU, this NVIDIA GPU, they contain 10 billion transistors. So it's something like 10 to the 14 transistors. So on the one hand, you can say, well, this demonstration breaks the quantum supremacy, we don't need quantum computers anymore, but on the other hand, it also shows what the quantum computer is able to do. By essentially using 53 qubits, you are producing a result that would take for
Emanuele, this is exactly the question about scalability, right? I mean, it's great. I mean, you can show it one quantum equivalent for transistor works much better than classical, right?
Yeah.
But the question is, you need, even for using quantum computers, you need a huge number of quantum operators that can work simultaneously, or they can do some more complex calculations. And then you need the scalability. Of quantum computers. I'm not saying quantum computers are not useful or something like that.
Okay, that's great.
I'm saying, no, that's what I'm saying.
Yeah. So I think the question that I would like to ask here or to address is, okay, provided that we can show these quantum computers can do a calculation, a simulation very efficiently, can we translate that into an advantage or in quantum utility? So the reason that people invest in those quantum computers is not that they believe in basic science, it's that they believe that these quantum computers can solve problems that classical computers cannot solve. And then the question is, what are these problems? Which problems can we hope to solve using a small scale or relatively small scale quantum computer like this one? So first of all, I would like to say that this is a huge question. No one knows the answer. And we put together a team of researchers, some of them are here, to establish a research hub, or to propose the establishment of a research hub, which we call kernel, which stands for Quantum Exploration and Research on Noisy Large-Scale Computation. And we had our first meeting here at Bar-Ilan a couple of months ago. So these are the people who are in the research hub, and we have representatives from all, most universities in Israel. And we hope that if the research hub is funded, then we can open it up to also other people who are interested in joining us. But at this moment, we are in this limbo that, okay, we submit a proposal, we don't have money yet, we don't know exactly. I'm optimistic, but there is a committee and that needs to decide. So I would like to now, I think this is the most interesting slide of my presentation, the most creative one, which is when I sort of asked ChatGPT to what he believes to be the uses of quantum computers. This is a summary of, if you go online, and you look for quantum computers, what can you do? These are possible answers. I think most answers will be in one of these categories or similars. The first time I gave this talk, I asked the people to actually do that exercise, ask GPT. That was a bad idea because then I lost all my audience at once. So I'm not doing it anymore. I'm giving you the answers here, which are, these are the different fields. And I would like to sort of tell you what is behind those keywords. And then I will focus on one of them, which is material design, and I will tell you a bit about a couple of projects that we did in this field. So let's start with logistics and finance. That's actually a field that I'm working on in this startup Quantimize that I'm a co-founder of. And so I believe I'm also quite an expert in this category here. And if you are interested, I can tell you more. But what stands behind the logistics and finance buzzword is essentially the idea of using a quantum computer to solve combinatorial problems. So optimization, to solve the optimization of combinatorial problems. So combinatorial problems are problems in which the number of solutions grows exponentially with the system size. So the typical example, this is not a very good example for us, but I think it's sort of, that's the most common example is the travel salesman problem, right? So that person that needs to visit one city, each city once exactly, and in the shortest possible path. And as you can see, if you have 3 cities, okay, you can do ABC or ACB, I mean 2 options. But if you have more and more cities, then you see that the number of options grows, basically the permutation of the number of options. So it grows exponentially with the number of options. The problem is, so there are 2 problems. And the first problem is that they are interrelated. So first of all, the first problem is that the quantum computer is expected to have an advantage in solving these type of problems. It's related for the experts to the Grover algorithm, so it's expected to have a square root advantage over classical algorithms. But the problem is that, so it means that it has only a polynomial speedup, it's not an exponential speedup. So whenever you have a polynomial speedup, there is a question of how you map your original problem into the problem you're actually solving. There is this whole concept of NP-hard problems, or NP-complete problems that you can map one to each other polynomially. So that's great. So it is true that if you could solve an NP-hard problem, in 0 time, whatever, independent of the size, then yes, that would be something. But if you have a good solver, one NP-hard problem does not necessarily mean that you have a good solver for all the NP-hard problems, because that polynomial advantage may be worsened by the polynomial mapping from one problem to the other. So it's really, how do you map? When I first started this initiative, this Quantimize, I said, my friends, I told them, we have an excellent solver of the Ising model. Eventually, these quantum computers are used to solve the classical Ising model. And then we went to companies and said, this is a great solver of the Ising model. And then he said, Ising what? So it's, what we believe as physicists to be the problem that is really interesting to the companies, it's not what there is really valuable. And the second problem, which is even more acute, is that, the NP-hard problem of the Ising model is finding the 2 ground state. To find the ground state of the spin glass model is NP-hard, but that's not what people care about. They want a good solution. They don't necessarily mean the best solution ever. If you're thinking of, being Amazon and redistributing your merchandise around, even if you waste 1% of your gas on traveling a little too much, that's not what will make that's not the reason why you want to invest in quantum computers. You need a good reason. So you need to look for problems that are very hard, worth a lot of money, and where the quantum computer can have an advantage. We have identified a few of them. But that's not the topic here. Also, there are IP issues, so I cannot tell you everything. But I just want to. So when I first showed this slide, these were like balloons, and I was popping all of them one after the other. And said, okay, 5, cool. You should color them as the Sipur Hamishta Ballonim, the story of 5 balloons, and popping them one after the other. But that's not what I want to do here. I want to say there are challenges. So I don't know. I mean, there is a challenge. It's not as easy as they want. It doesn't mean that you cannot solve it. So cryptography, it refers to these breaking RSA, so that's something you probably all know. Whenever you go on the internet, you write HTTPS, right? Otherwise, your IT department will be upset at you. And the reason why I use this HTTPS is that it means that it's encrypted using the RSA algorithm. And the encryption RSA algorithm is based on the idea that factorizing big numbers is a big problem and becomes very hard for big numbers. And in principle, quantum computers have an algorithm called the Shor algorithm that can factorize numbers very quickly. And so it could give an advantage, and they can be able to read all your emails. But the problem is here, there's also a challenge, and the challenge is that people know about it. So people that have real secrets, they do two things. Either they speak about them at the radio, they use it, tell it to everyone, or alternatively, if they really want to encrypt it, they will encrypt it using more sophisticated method, those post-quantum encryption, which are presumably safe from attacks of quantum computers. So that's, it's a question of, okay, we will be able to build the quantum computer, but when? If you build it in 100 years from now, and people will be able in 100 years from now to read our emails, that will be fun, but not worth a lot of money. Sure, if you can break RSA tomorrow, then, well, that could be groundbreaking. So there is a question of timeline. AI probably is not just because it's a buzz, and quantum is a buzz, so the Google team is called Quantum AI team, so you have two buzz together, right? It cannot be wrong. I think there is a challenge here, which is related actually to the clock of the quantum of the quantum computers. So I mentioned there are different technologies which differ in particular in the fidelity of the gates. So let's say trapped ions have a fidelity that is on average much better than superconducting circuits because they're much more reproducible, right? All the atoms are born equal, while the superconducting circuits, you need to manufacture them, and there is always some imperfection in lithography. So that's why trapped ions are one possible reason why trapped ions are much more precise, but they are also very slow. I mean, the time that it takes to do an operation in trapped ions is on the order of even a few milliseconds. A few tens of microseconds. So the clock rate is between 10 to 100 kilohertz for a trapped ion quantum computer. That's compared with the clock of our classical computers that runs at 2 gigahertz. So there is many orders of magnitude, which means that if you try to just naively take all your big data and try to feed it on the quantum computer, it will take forever. So that's probably not the way to proceed. Maybe one can combine machine learning and AI. There are different proposals. We also worked on a project with the Makmal on this. And there are some ideas, but one needs to understand that there is a problem of how you take all your big data and you put it in the quantum computer, how you store it in the quantum computer. So that's not trivial. Drug discovery refers to quantum chemistry, and here the problem is that most of the people who speak about quantum chemistry are mostly physicists. And whenever I hear a physicist speaking about quantum chemistry, I become worried. Because physicists don't really know what chemists are worried about. I think we all a little bit overlook at chemists, but actually chemists are very good at their job, and they develop very advanced numerical techniques, and they can simulate right now pretty large molecules, understand what their behavior. So it's not that if you can solve the molecule of water, it will have any impact.
But they use approximations. Not that they don't do it.
Absolutely, they use approximations. Just saying, these approximations are very good. So it is a challenge. I mean, people usually use the analogy between classical development and classical computers, which now completely change our world. At the beginning, it was just a calculator. The point was that at that time there were no other calculators. So when the classical computer developed, even if they were able to just multiply two numbers, that was already a big deal. Here, if you can solve the molecule of water, it's not a big deal. People know how to solve. Even relatively large molecules, chemists know quite well how they behave. So if you want to make an impact, you need to go to big molecules.
They cannot solve relatively, I wouldn't say easy to solve because they cannot. But there are some well-known problems like super cooling in water, which is no solution. I mean, very
I'm not an expert. I'd like to hear more from you about this. My understanding is that if you want to solve, I mean, I read a couple of reviews on quantum mechanics. Said, yeah, sure. They said if you want to solve a real problem, you need a very large quantum computer, say million of qubits. And then they say yes, but there are other things that you could do with. So that's why I have this. I'm saying I think there are.
And also, my point is that they're very good. They can solve many hard problems. They cannot solve everything. There are still many
Absolutely.
hard problems.
No. Yes, absolutely. That's absolutely right. Yes, it's just saying you need to go to those problems that cannot be solved using other methods, and these are hard problems. That's yes. I perfectly agree. Yes, thanks for the clarification.
So, what's the difference? I'm not sure I understand the difference between quantum chemistry and material design. It sounds like two sides of the same coin.
Yes, they are two sides of the same coin. It's a little bit about like the question of what is physics, and I think the best answer I found for the moment, maybe you have other ideas, is what physicists do. So this is what chemists do, and this is what physicists do. I agree, they are very much interlaced, they are very much connected. It's a little bit of a different, but I agree, they are like two sides of the same coin. So when we speak about material design, we speak about quantum simulations. And here I would like to say, and I hope I will not upset, say Efrat too much. But I think there is a problem in condensed matter physics, which is that we like to solve models, like say magnetic spin models. At least that's what I like to do. But then the relation between that and real material is not always obvious. So I'm saying I think there is a challenge in knowing what is the model behind material. So people always give this example of cuprates, which I personally don't find very, very interesting. And they say, okay, if we could solve the Hubbard model, then we know how cuprates behave. And I think this is not necessarily the case, because even if you can solve the Hubbard model, which we can discuss if you can solve it using a quantum computer or not, but if you can solve it, it's not clear that this is the description of cuprates. So even if you know how that there is D-wave superconductivity or that there is no, it doesn't necessarily tell us something about cuprates. Not to speak about that understanding the material does not necessarily mean that you know how to produce new materials. I mean, people speak in the news about we will design new materials, but it's not obvious that from solving a model to actually building a new material, I don't think there are many steps in between that needs to be addressed. So again, I'm highlighting the challenge, but that's what I think. So okay, so what I would like to tell you today is about to focus on the quantum simulations. So you all know the idea of quantum simulations, what was put forward by Feynman. He said, well, you have a quantum problem, you try to solve it classically, it doesn't work, there is a sign problem, these are complex numbers, you cannot simulate it classically, just use another quantum system. That's the idea of quantum simulations. And that's something that if you look into the recent publication, high-profile publications using quantum computers, especially from the Google team, you will find that most of them are related to simulations of interesting physical models. I pick up two here which were made into the headlines of newspapers. One was about a new form of material, this time crystal, and the other was about the quantum wormhole. And people got very scared that the quantum wormhole has a black hole in the middle and will annihilate our entire universe. And to them I tell, don't worry, this is a simulation of a model that is somehow related to quantum wormhole. It will not destroy. There are other better ways to destroy our world. So if we look into more recent applications from the last year, I would like to highlight these two works. The first one is about topological Floquet order. So they simulated a two-dimensional model in the Floquet regime. I will mention Floquet in a moment. And they were able to see very nicely these edge states going around, the defects, and it's a beautiful work. And there is another work related to Floquet prethermalization. This is a work in which they actually make the claim that simulating those dynamics on a classical computer is at the edge of what can be done. And the people who did the numerics are, very good numerical experts in numerics, Michael Knapp and others. and they tend to believe what they say. So they believe that we are we have really achieved the point where simulating those models, specifically the Ising model, on a quantum computer becomes really, simulating that using a classical computer is on the edge, on the verge of utility. So what we have done in our group is we have done what I call the poor man's quantum simulations on the cloud, because we don't have enough money, so we are poor. And what I've been telling my students is that we are writing a poem with 6 words and 6 letters. So, we have very little, these quantum computers are very noisy, so we can use only a few qubits and a few gates, and then we lose track of the noise becomes too large. And still, if you think about it, you can write quite a few poems with 6 words of 6 letters. And that's what we've done for the past 5 years.
So you gave the most unmotivating motivation in the beginning of the introduction. So why do this now? Because now I'm puzzled.
Yes. So thanks for the question. I'll address it in a moment. So these are some of our recent works in which we simulated some model. So something about one topology in 1D, non-local games. This was a very cute experiment with 1 single qubit. This is something that is related to Bose-Einstein condensation. That's more quantum information, how we encode the state, and this is about error detection. So actually this was a lot of fun because it's actually in collaboration with Surin Das. So the student came, he came and said, okay, I have an idea, we can make error correction and correct 0 errors. What? What do you mean? What does it mean to make error correction? And then what I understood after that was my contribution, basically, I think, to the project, was that what it really meant is that you can detect the error. You cannot correct it, but at least you can detect it. So that's like a first step towards error correction. So these are these works, and what is unique about these works is that in each of them there is some experiment that was performed on a quantum computer on the cloud and gave some reasonable results which we could analyze. So now let's address Hanan's question, which is why is this useful? I mean, after all, these are small systems. Why cannot you simply simulate? So I would like to give 3 partial answers. First of all, I think it's really nice, sort of, to think that yes, I can realize it. I think these quantum computers really give us a different perspective of quantum mechanics. After all, this is the same Schrödinger equation that you studied in your undergraduate, or if you want even linear algebra, where you multiply complex vectors. What is unique here is that there is a question. You can ask yourself, what can I see on the quantum computer? Because it is true that it's very tunable, but it has limited depth, limited measurables. So it's very rich, but also limited. And you can ask yourself, how can I see that effect? If I have in mind some effect, what is that I can realize? So it really gives you like a little bit of a different way of thinking, which gives rise to new questions. Like the question of quantum state encoding, you could have asked it, 50 years ago. It's not completely new, but when there is this particular structure of quantum computers, for example, the fact there are gates, and so it gives you really a unique approach to these quantum problems. So that's number 1. I think number 2 is that, in fact, the quantum computers do not behave as they should. So there are very interesting questions about the noise, or to study the noise, how you can mitigate the noise. I will tell you a little bit about error mitigation in a moment. So there are, in fact, the discrepancy between the real experiment and the theory. I think this is also interesting to study. And the third answer is that eventually this is an experiment. So the way I like to think about it as a physicist, it's not like a machine that performs for me a calculation, but really as a quantum system. And I would like to apply my theory, understand this physical system. So that's why it is important eventually to reduce them to see whether what I believe them to be is there or not. So I think there is really, I think for a theorist, it's like a new experiment. I mean, when you create a new material, you want to study its properties. For me, this is like a new material. Let's study its properties. So I don't know. I don't know if I would have built those quantum computers to begin with, but once they are existing, I think it is very interesting for us to try and study them and understand how they behave. So these are the different, from a more, theoretical perspective to really physical questions. And there are also questions, like there is a project that David, my student, is currently working on, which is about something called the crosstalk. So the fact that the qubits actually talk to each other if you don't want to them. So there is really physical questions related to the system itself that you can try to address. So that's, I think. In addition, I think, it's a trendy topic. It brings students, it brings funding, and I think, we also want to do things that are cool, right? We all do it. We work on topics that are hot. So why not? I mean, I could have studied different type of quantum mechanics. This is one of them. So I think that's what I think. Why I think it's interesting. So the two projects I wanted to tell you about, and hopefully we'll have time only for the first one because the second one I'm not really sure about it. Is two examples of dynamics of the one-dimensional. Actually, not the one. Two dynamics of the Ising model. So forget about one. So the first one is, so this is the menu for today. Let's start with the first one. So the first one is actually an experiment from 2023 from IBM. And they said, they were the first one to say, we have quantum utility. We can do something useful out of a quantum computer. What is it? What we can do, we can simulate the two-dimensional Ising model. The dynamics of the two-dimensional Ising model, you all know the quantum Ising model, coupling and X, this is well known. So this is actually the quantum computer itself, schematically. Each of these black dots is a transmon, some superconducting circuits, and they are coupled according to the topology that you see here on the board. Now, there is an important caveat when using quantum computers that, as I mentioned, they are built out of gates. So it means that you would like to simulate the dynamics of e to the IHT, right? To simulate the dynamics of, let's say, static Hamiltonian. But you cannot. Why? Because you know how to simulate Z and you know how to simulate X, but you don't know how to simulate both of them together, because this is a type of gate, it's a 2-qubit gate, it's a single qubit gate, and you have calibrated each of them separately, but you don't know how to apply both of them together. So what you can do instead is to do a little bit of each of them, what one could think of as a Trotter expansion. So you take this continuous time evolution and you split it into small periods, small steps. And so what you really do, you apply a little bit of X, then a little bit of Z. Actually, even the Z is a little bit of a problem because you cannot apply a ZZ gate between all the two qubits together. So let's say, if I apply a 2-qubit gate between these two, these red two, I cannot apply the same time between these blue two, because you cannot use the same qubit for two gates at the same time. So what you will eventually do, this is the reason for the coloring, you will first apply all the red gates, then apply all the blue gates, then apply all the green gates. Quantum mechanically, it shouldn't affect too much because these gates are commuting with each other, so theoretically it shouldn't make much of a difference. What does make of a difference is that you apply first the X, then the ZZ. And because these two don't commute, then it's not the same as applying them together. Yes. Okay, good. So let's now look at the results. So this is the first result that was published. What you see here is the average magnetic field of qubits. So I refer to the qubits as spins. So 0 would be spin up and 1 would be spin down. So what you initially, all the qubits are initially at 0. And what you see on the x-axis is the magnetic field. So the H that I'm applying. Remember, there are two parameters. What is nice about this model is there are only two parameters, H and J. So they took J to be a specific value, I think 5 or 2. And so actually what matters here is J times the delta T, right? What the time that step. So how much you're applying. So you're applying, it's an angle essentially. So you're applying, an angle with a rotation. This is essentially a rotation around the x-axis with some angle. And that's the parameter x of this plot. So here I'm essentially not rotating around the x-axis. So you see all the spin initially pointed up. You have only ZZ gate, so they stay there. There is nothing happening. This is why at H equals to 0, the magnetization is exactly 1, because they all point up. While when you change the magnetic field, well, changes. Actually, pi over 2 can also be easily solved because it turns out that at pi over 2 there is a special property called Clifford. So the circuit at pi over 2 is a Clifford circuit. So actually, this point you can also compute exactly, and it's exactly 0. So this is exactly 1, this is exactly, and there is a curve that connects them. And the question is, what is this curve? So what you see here are actually two plots. So you have the black one, which is the exact solution, and the green one, which is the experimental one. So I didn't mention that this is after doing exactly 5 steps. So you do 5 steps with here magnetic field.
What is the y-axis?
The y-axis is the magnetization of the qubits after 5 time steps. So they initially are all up, you apply those gates, they do something, and then you compute the magnetization after 5 steps.
Okay, you mean just spin up and spin down whatever?
Yes, you probe them, and on average, you give.
The average,
yes, and this is the average magnetization.
And
Yes.
the exact again
Is a result of numerics. Now, how comes that you can do numerics for such a huge system? Because there are 127 qubits. So naively you would say, well, you need 2 to the 127 transistors or something, which is unreachable. The reason is that this circuit is short. So there is a light cone effect. I will mention light cone after, also in the second project, but there is a light cone effect. So the correlations cannot spread beyond a certain amount. And so eventually you really need just to simulate a small system, a much smaller system. Because initially all the qubits are decoupled, there is no entanglement between them, and the maximal entanglement that you can reach, which essentially sets the size of your tensor network, is limited by the fact that the time steps are only 5 time steps. So the most you can couple, you can entangle 5 qubits, not more than that. That's the idea. So for 5 time steps you can do that exactly. Again, it's an approximation, but it's an approximation which is exact, because you are truncating something that is 0 beyond the truncation level. Yes.
Do you know what's missing in the experiment?
Yes. So so what you see here are so as you can see here, there is a large discrepancy between the experiment and the theory, although they sort of go in the same direction, but there is a discrepancy. And what is beautiful about this experiment is that they are actually able to do what is known noise mitigation. They were able to kill all the noise in a method that I will tell you in a moment, which is really cute. And in fact, these blue curves, these blue dots here, are actually the result of the experiment with noise mitigation. And they fall on top of the theory. You can actually, if you look closely, you will see that actually they even give you a little bit of an unphysical result, because this blue dot is beyond 1, which cannot be because the spins point up. So the 1 is the maximum. You see that the blue dot is a little bit above, that's still fine because it's within the error. So it's not, but you see that the blue cannot be an experiment, it cannot be an experiment, it cannot be a theory, because it goes beyond what is physical plausible, and yet it's the result of an extrapolation. So the method is called zero noise extrapolation, and I think it's a very nice method, something that also Kerma, the company of Emanuele and Torre,
Something without any more.
yeah, in a moment, I'll tell you.
No, I mean, you sound everyone.
No, one second. I'll tell you. So this is something that Dorite, Kerma is also developing a lot. What is the idea of zero noise extrapolation? So the idea is the following. You would like, so I give you an example. So let's say you have a student that is doing numerics, and he does numerics for n equals to 100. Comes with a solution, and then you say, okay, it's sort of nice. Let's start this finite size scale. So after 1 month, the students come back and he says, but I'm sorry, I cannot go beyond 100. And what you tell him or her is, no, what I meant is go, to smaller systems. So, sometimes it's useful to extrapolate on the other side that you think that you would do. So here what you would really like to do is to kill the noise, but the zero noise extrapolation method that works is actually based on amplifying the noise. So how this is done? In 2 steps. First of all, you characterize very well the noise. So you do a lot of calibration. It takes a lot of time, money, on the quantum computer, but you calibrate for each 2 qubit gate what is the noise very precisely. Then you repeat the experiment.
What do we characterize in the noise?
The noise, so what, okay, the way you do it is by using Pauli matrices. So you know that, let's say, a 2-qubit gate is supposed to do a control node. Control node is one of these quantum gates. It's not doing control node, it's doing a little bit of a different gate. So you characterize the gate that is really doing rather than the control node.
So eventually you have kind of a list or something.
Yes, you have a list, exactly, a list of all possible noises with amplitudes. Okay, and you do it for each gate separately. Then what you do, you repeat your calculation with additional gates that mimic the noise. Okay, so let's say I have, instead of having 100% noise, I now have 150% noise. How? I have the 100, well, there is nothing I can do with that, but I also add random gates that simulate the noise. So it's really done on the quantum computer itself. This is what is beautiful about the zero noise. It's not just post-processing of the data. You really do, you really do more circuits that have more gates and more noise.
But can you find a rule that describes the noise? Or, because, for experimentalists, if I can characterize the noise, I know the distribution of the noise. Can you say something about the noise?
Yes.
Because if not, I always fail to...
So I think, the assumption, there are two assumptions. One assumption is that this is a Markovian noise, meaning that yes, and the second is, so basically, yes, if it's not Markovian noise, there are ways to make it Markovian.
As long as you can find a rule.
Yes, so the rules are Markovian and local. So you assume that the noise is only between the gates that you apply. You assume that there is no noise that connects two qubits that are separate. So it's only either single qubit noise or 2-qubit noise between the gates that you apply. But this is if you want the observation. So if your model of the noise was wrong, then this would never work. If the noise of the model works, this is what you see. So what is hidden here is beyond the green curve, there are other colors, which are the colors that perform the same calculation with more noise, 100%, 150, 200, and then you extrapolate that to 0. So for each value of the magnetic field, you do many experiments with different values of the noise, and then you trace it back to 0.
I know this doesn't make any sense.
This is, Michael, have you said it? Because this is exactly what I thought when I first entered into this field. But
No, there's interaction between two qubits, which is going to be random due to quantum mechanics. Sometimes you get it one way, sometimes the other way. It's not noise. That's just the randomness of quantum mechanics.
yes, no, that I agree.
Then there is interaction to the outside world, which brings you noise, which is totally unpredictable. Because a photon comes in and hits one of the qubits or something,
Yes,
and that's real noise.
Yes, yes.
I'm not sure which noise you're talking
yes.
about.
So yes, I agree. So
That's
the
not
noise I'm talking about is not the quantum noise. I agree with you. It's the classical noise that is due to the environment. So essentially, we want to
But
describe.
that's not constant. That's not changing.
Exactly, it's a random noise. So you describe it using these Krauss operators, which are just random.
Yeah.
So for 2-qubit gates, there are as many possible gates that you can. So basically, you build the basis of all the possible noises. Okay, so for
You
2
can
qubit.
simulate. You can simulate.
You have to do something about
You won't
the
get the exact.
environment.
You won't get the exact result of the experiment,
Depends.
but you get the tolerance.
Why? Depends if I do it in the sunlight or I do it
No,
in the
but
dark.
okay, exactly. The assumption here is that the noise is constant over time. So you are right that to do this experiment, that you will. Well, this is for a specific quantum computer in specific dilution fridge. I can guarantee you that if you warm it up and cool it down, it's completely useless. So the system will change completely, and everything you've done, you can throw it to the trash. So this is very, 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 very sensitive. You need to assume that this is done fast enough so that the system didn't change too much. I perfectly agree with you that if you change the conditions, the temperature of the even the input, the waveguide that you're using, these microwaves that you're using, whatever, will be completely different.
It maybe also will not work even if you try to do this.
Yes.
No, it's hard.
Yes, it is, but this is why I'm actually spending so much time on something that I didn't work on, because I think I was honestly surprised. It works. I mean, you cannot you cannot fake it. This is what it is. But there are many assumptions. I mean, that's exactly one. You need to assume something about the noise, and one assumption is the energy. Now, then what they said, look, we can also, I told you this is for 5 time steps, I can do the same for 20 time steps. And if I do it for 20 time steps, then the computer will have a little bit more of a noise. So you see that also in this case, the green, the red is probably the theory or something. You see there is a larger discrepancy between the noise extrapolation and the the noisy result. So the system is more noisy, but still you get a curve, which is this blue curve. And then the claim of the paper was that there is no possible numerical method that in a reasonable time will be able to characterize those systems, and that's why they said we have a quantum utility because we can mimic the two-dimensionalizing model better than any classical tensor network method. Yes?
If you know how to extract the error bars?
So the error bars essentially is done so I told you there is noise and there is the average magnetization, and you have 100%, 150% and 200%. So you have 3 dots here, and you need to extrapolate to 0. So for this extrapolation, different models will give you if it is linear or quadratic. You can sort of evaluate how you extrapolate back to the. Again, it's not a guarantee, but it's an indication, and it's consistent with what they say. Here the result. This is one exactly, and it's consistent with other observations. Okay, so that's the way that.
So how do you get values above 1?
Well, because you see, if I extrapolate something that is smaller than 1, then I have an error. Maybe I can, I can overshoot.
Oh, because you start with big numbers, and then okay.
Yeah. So I mean, all the physical observers were below 1, but when you extrapolate it, you could cross 1. Okay. You see that? Okay, good. So that statement was correct for 2 weeks, because within 2 weeks, several groups applied more advanced numerical methods. And they were able to actually reproduce those results. So these are 3 different papers. They are using advanced tensor network problems. This paper here is actually interesting because it's using essentially a perturbation over Clifford gates. So what I'm trying to say is that there are ways to do it. It's not trivial. It's not that you can just compute it on a classic. You need to either use very advanced numerical methods or use some smart tricks in approximation. That's why I personally believe that this work was useful. Okay, by the way, the result is that indeed, you see this is the experiment and the blue curve is the theory, and it matches perfectly. So, I mean, the experiment was correct. I mean, the predictions of the experiment were correct. The only problem was that they said there is no way to do it numerically, and people showed how to do it numerically. But that's the way that science advances. And I personally believe that this was an interesting experiment because it really helps people develop new numerical methods by, not just for fun, but when you have, a specific goal, it's easier to develop new methods and go into specific, when you know where, when there is a question, puzzle. So I think this was a really nice experiment. So what I did was to ask this question. So you see this curve here looks like simple. I don't know, maybe it's a cosine. That's what I was looking at this curve. It's simple. Is there a way to give a simple description? Maybe not precise, not a numerically exact, but something that also, why does it go down? That was my sort of question. What's the physics? This is my way of understanding physics. So what I did, I said, what if I use a mean field? So mean field means that this is the gate that you're applying to the computer, the X gate and the ZZ gate. And when you do mean field, well, I guess we all learn mean field from ASA, which we all miss. So that was just a point to mention our big teacher, where I personally learned about mean field. And what mean field is about is, instead of having 2 operators, you have the average of the operator times an operator. So it means, actually in quantum computing language, it's very simple. It means that from a 2-qubit gate, you're transforming into a single qubit gate. So you now have just a single qubit that you apply on single qubit gates. So it just becomes a 2x2 matrix, which is something that you can basically do analytically. So the mean field itself, you can essentially do it analytically, And the idea is that you can do it self-consistently. So you advance one step, then you compute what is the average Z. You have the average Z, and then you apply the next gate, and you do it several times. And this Z, which is the connectivity, is basically, here I use the total number of gates divided by total number of qubits. So that's the average connectivity of each qubit, which in this case is 2. If this number was infinity, then the mean field would be exact. So it's not, as Asa taught us in the book, sometimes you can use a large edge expansion for n equal to 2. So also here, this Z is the real Z is about 2. But I use a method that would work for the Z that goes to infinity. The method itself doesn't work very well. Okay, I lost that. Okay. So again, what you see here is the exact solution in purple, and the green is the mean field. You see it's oscillates. It starts okay. So the first feeling was, okay, I'm onto something. There is something in this story, but not the entire story. So the question was, how can I improve it? And the way to improve it was to look into fluctuations. Yes?
Just to make sure I understand this model, so in
Yeah.
principle, if you evolve it in time for more steps, it will oscillate. So you start with the Z and then it will go up and down.
Well, there are two. So there are two rotations. There is an X rotation, and there is a Z rotation. So that's the model. The model has an X rotation and Z rotation. Yes, it oscillates forever. These, oscillations that you see here, which are order 1, are exactly the rotations that you are applying. So yes, it doesn't.
I'm not talking about the oscillations of the error, but
As a function of time. No,
as a
well,
function of time.
yes, a function of time. The
curve will-
qubit will oscillate randomly, essentially, on the Bloch sphere. That's what will happen. Now the idea was to add fluctuations. And the simplest way to add fluctuations is to say, well, there is the average Z, but there is also fluctuations in Z. And what is nice here is that two things. First of all, I can evaluate what are the fluctuations. So if I assume that each neighboring qubit is a qubit, it's a binary variable, and I know what is the average of the binary variable, I also know what is the variation of it. So the fluctuations here are determined by the average value of the qubit, which is something that I already have. So I don't need to build new diagrams, I just compute the average spin, and then I can compute what, just as a binary variable, I compute what is the fluctuations. In addition to that, what you see here is that when I write this like this, what you see is that I have a rotation around the z-axis, plus a random rotation around the z-axis. And now this model of a random rotation around the z-axis is a model that is well known in the quantum information literature for describing dephasing. Right? Dephasing is that process that you dephase in the xy plane. So it's really a random rotation on the z-axis. So you can formulate it you can compute not only you can simulate numerically this, but you can also compute what are the average expectation values by working in a density matrix formalism using Krauss operators. So you can introduce this language of noise to simulate actually the dynamics of unitary systems. So this is what is nice about this project, that we started from a system that is a closed system. I'm simulating the ideal quantum two-dimensionalizing model, and I end up with this model that is one qubit with noise. That's what I like, and I think it sort of works. Yes. Bye-bye.
Yeah.
Okay. Oh wow. Wow. Sorry, I didn't look at my watch. Okay. So it sort of works. I really didn't have time to speak about the second project. So let me conclude. I told you about Quantimise. I do want to tell you about Smart Archive. I see many faces here who are not subscribed to Smart Archive yet, so I suggested to do it as soon as possible. And that's what I wanted to tell you about today. So I told you about dynamics of the IC model. I told you about the project where we used something that goes beyond mean field to describe. So this is this orange curve here. You see, the orange curve is following. It's not exact. You see, there are some spurious oscillation, but it's sort of following the same physics, in my opinion, better than the mean field. You can also extend it beyond mean field. It will become essentially dynamical mean field theory. And there was another project that I didn't tell you about by Mona Lisa. By the way, this was a work with Mon, and I didn't tell you about the work with Mona Lisa that studied the propagation of small perturbations in a one-dimensional chain, so studying the effect of light on propagation. Okay, thanks.
Okay. Questions? Especially students? No, wait.
I have one.
Oh, yes.
Maybe I can ask. Why does it match that small value of h? The main field.
Here, this
No, in this side. Like on the small h side here.
Okay, yes. So that's a good question. And this is also related to trying to sort of, can we intuitively understand what's going on? So remember that you initially start with all the qubits polarizing the z basis. Now, this is the rotation around the x-axis. So that's the rotation. So in this region here, the spins are mostly polarized. You depolarize them a little bit. So the fluctuations are also small. The fluctuations are second order in the angle of rotation. There are two effects. One, which is the average spin that you are changing. But as I told you, when you change the average, you also change the fluctuations. But the effect of fluctuations is small because the spin are mostly polarized. So if you are up, the fluctuation is exactly zero. So that's the idea. So yes. Yeah.
It's like what you think that the kind of qubit is the most consistent in the future? Now and in the future.
Easy questions there.
So yeah, this is. I can tell you there's a lot of money involved around this question. So one needs to be very careful, I think, when expressing. I think the safest question is really I don't know. The second best question is it probably depends on which application you have in mind. Because I mentioned the different technologies have different advantages. Let's say ions. If I compare, for instance, let me tell you the following. The three main technologies that are mostly invested in are trapped ions, superconducting circuits, four. Trapped ions and neutral atoms, superconducting circuits, so like quantum optics, more condensed matter, superconducting circuits, and there are then photons. Okay. The superconducting circuits are good, but there is a problem of scalability. One doesn't know how to go to very large system sizes. The same is true for ions. The ions are also very slow. The advantage is that the precision is very high. They can reach very good fidelities. The neutral atoms in physics are much easier scalable. The problem with ions is that they are ions. They have electric forces that are very strong, so you need to confine them very hard. Neutral atoms are neutral, so you can pick them up with a laser with these optical tweezers. In principle, you can think of multiplying them a lot, so it's easier to scale. They're relatively slow because you need to take an atom and actually physically move it to a different place. I'm very surprised that it works. It still sort of works. I think that the big question is photons. So photons, for the moment, they didn't really even show clearly a single qubit gate. So it's not very clear what will happen. But there is a big question mark because they say, well, photons are very easy to generate. So if I know how to handle, they're also very fast. So if I know how to handle them, once I know to do that, then the path towards success is will be very, 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 very fast. But it's a question. I mean, if you haven't shown,
You need nonlinearity, which is hard to get with single photons.
yes, yes, no, it is very hard. That's certainly the case. The question is it true that once they can handle one, they will be able to handle a million?
To get the ones.
Yes, exactly. That's what people believe. There are also other. I didn't speak about other technologies.
Since we talk, I will mention your company is simulation. We have a lot, and I will show you how many experiments with use different platform. So how do we use the platform? We have
Via the cloud, yes.
how do we use that? We should pay a platform or they have some website and we use it for free.
So yes, IBM is, for instance, offering to use a quantum computer for free for a certain amount of time. I think that the tendency is that the more time goes on, the less easy is to get free credits. At the beginning they were very generous, and now you need to argue that this is a good project, so it's becoming hard. This is also why we established this center, the kernel center. One of the ideas is to have a budget to actually buy quantum computing on the cloud resources. So there is a question. For the moment, I think the costs are affordable because there is no real industrial use of quantum computers, which means that the only users of quantum computers are research teams, either in the academia or in the industry. And they have a finite budget. So as long as we have a budget that is similar to other teams in the world, we are competitive. If at some point the quantum computers will become useful, then forget about it. But that's also why, for instance, Israel is investing in building a local quantum computing center that will be always accessible to, but they also charge money. So, yeah.
Okay.
I'll ask.
Yeah, I think we're already a bit over time, so let's thank the speaker again.
I want to tell you a little bit about history. 55 years ago.
One second.